Hey guys, welcome back to another RS Game Maths video, and in this video I'm going to be showing you guys a technique of factorization which allows you to factorize large odd numbers without actually ever having to do a division sum. So let's get straight into it. Now it's called Fermat Factorisation, and this has actually come on from previous step questions, so you can see that it's really useful to know about. And basically what it is it utilizes the algebra identity a squared minus b squared is equal to a plus b times a minus b, also known as the difference of two squares. So what it states is if you have a big number, let's just say odd number n, if you can find out a way to represent n as a difference of two squares like this, then you can obviously find factors because these are just going to be the factors like so, these two factors. So what this really means when we're trying to work it out is we just want to find something like a squared minus n is our big odd number, is equal to b squared, like so. That's what we're really trying to find. So if we can find a situation which satisfies this, then we can find some factors. And I'm going to show you guys how we can do this in this video. So let's first have an example. Let's say n is equal to 33127. So you want to find the factors of n. Find n's factors. So what we can do to get a starting point is we can just take the square root of n. So I'll take the square root of 3317, and that's going to give us about 182, just round. So this gives us a starting point. Now what we can do is we can just find numbers around this which satisfy this inequality, which satisfy this. So let's just try 182 squared. This gives us 33124. So the difference between this and this is equal to 3. So that is not a square. So now we might try another number. Let's try 183. And we'll just try this. Obviously, you might also go in the other direction, like 182, 180. Those can also give some valid solutions if your situation arises like that. But I know the right answer, so I'm just going to point us in the right direction. So let's try 183 squared, and this gives us 33489. So the difference to n is now going to be 362. Well, it's actually going to be minus 362, but sorry, this one should have been minus 3. But yeah, the difference is now 362. And now let's try one more time, because 362 is not a perfect square. So we'll try 184 squared. 184 squared. That gives us 33856. And now you'll see the difference to the original n, when we subtract it, is actually 729. And if you know your square numbers, you'll know 729 is a perfect square. It's actually the perfect square of 27. So we know, since we can write 184 squared minus n is equal to 729, and we know this is equal to 27 squared. So now you can see how this can be used to work out some prime factors. So with a bit of rearranging, like so, we can get it n is equal to 184 squared minus 27 squared, like so. And now what you can see is this can just be rewritten 184 plus 27 and 184 minus 27, which gives us the two factors 211 and 157, like so. Nice and easy. So we've managed to find some factors of n, and you can see if you were doing this by trial and error, like so, just dividing out random factors, 3, 5, 8, 11, 13, 17, like so. You wouldn't have ever got to this, although it would have taken you a really long time. And the thing about these is that they're both primes, so there's actually no other factors of n other than these, so these are the only other factors of n apart from 1 and n. So you can see how useful Fermat factorization was for working out that one. Now I'll give you one more example, and hopefully you can understand how to do it from there. And also, yeah, okay, so let's do one more example. Let's say n is now equal to 5,959, like so. So first thing we're going to do again is we want to get the starting point. So we're going to take the square root of n, like so. And that's going to give you 5959, which is going to be about 77. So this is our starting point. Now what we can do is we can just start trying out numbers around 77. So I'll go in ascending order again. So 77 squared, well, that's equal to 5929. So the difference between them is actually going to be 30, which isn't a square number. So we'll try again. Let's do 78 squared. And this is going to give us 6084. And also the thing is, I don't think we can actually have negative numbers here because the difference is actually going to be negative 30, which you're not going to be able to get that from a square root. So not sure that they can actually be negative numbers. So that's why it's pretty important. That's why I think we should always be ascending, because this difference can't actually be negative. But anyways, back to this. So 6084, and the difference between these is 125. So it's close to a prime number, but it's actually not. It's a cube number. So if you can find a way to represent this as a cube, then you can use difference of two cubes, but otherwise that's not valid. So let's try 79 squared now. 79 squared is equal to 6241, and the difference between that and the original n is 282. So again, not a square number. It's close to 17 squared, but not really, not exactly. So now we'll do 80 squared, and we all know that this is 6,400. And let's see if that gives us a perfect square, and it gives us 441. So there we go, we found our perfect square, because 441 is 21 squared. So again, now we can just do the procedure. Basically what we found is n is equal to 80 squared. Sorry, let me just read. What we found is 80 squared minus n is equal to 21 squared, right? And this comes back to why this can't be a negative number, because if the difference was negative here, then we wouldn't be able to square this into any term like so. So that's why I believe the difference has to be positive. But yeah, so we managed to find 80 squared minus n is equal to 441, which is 21 squared. So now let's rearrange this into n is equal to 80 squared minus 21 squared, and now we can use difference of two squares. 80 plus 21, 80 minus 21, which comes out to 101, and it's 59, like so. So there we go, we managed to find more factors of 5929. And I'm not actually sure if these two numbers are prime, but actually I know 59 is prime, so it's likely this one's prime as well. But yeah, thanks for watching, and that was how you complete Fermat factorization, a factorization method which allows you to factorize without ever having to divide. Notice how we never divided in any of these sums. We used all the other operations, but not dividing. So thanks for watching, and I'll see you guys in a future video. Bye.